Hello everyone, welcome to the second part of the Generative Model series. These tutorials are part of the Computational Design Basics course at the Digital Design Unit at the Technical University of Darmstadt. In the first part of the Generative Modeling series, we built a parametric tower and performed a basic analysis of it. And in this video, we're going to start building out the generative part of this model. So let's get started. I have my Rhino and Grasshopper open at the previous state. So just a quick recap. We used the Sears Tower in Chicago as a reference, 9 tubes in a bundled structure. We have 8 sliders that define the height of the tubes on the periphery, and the core is always the maximum height. Those values are used to build a 3D model of the tower, which is here. We also use the numerical way to calculate the area of the tower. And we built a rudimentary sun system where we can define the sun position on a dome and calculate the vector from which the light falls on. Then we project the shadow, which is here, given the sun position, and we also calculate what part of the shadow lies over the neighboring part and the neighboring building. At the end, we have 4 values that constitute the way we evaluate this model. The floor area, the total shadow area, the park shadow, and the neighboring shadow. So what we want to do next with this model is to actually start generating more than one tower and evaluating those options. Let's start by duplicating the whole model and disabling that part where it's only about a single tower. The simplest way to approach creating multiple states of that model is to try and connect another set of sliders to the input for the values of the building. Basically, the building is defined by these heights. Nothing else is influencing its shape. I'm going to copy the sliders and quickly connect them, holding the shift so that the old ones don't get disconnected, to the merge component. There we go. If we check the output of the merge component, we'll see that we have one list of 16 values. What we need is actually 2 lists of 8 values each. A way to achieve that is by grafting the input here on the merge component, and Grasshopper will split that into 3 for us. This works for us because instead of getting in a list of 2 values on each input, when we graft it, we get a tree with 2 lists, each list having 1 value each. And when Grasshopper merges all these inputs, then these 2 lists of 1 are merged 8 times, are merged into 2 lists of 8 values. Okay, so let's see what happens further down, the definition. Here we are sorting each of these lists of 8 points, and we are finding the highest tube in each particular version of the tower. Here it is. We have once 104 and the second time 104. This is because all these sliders are the same, so let me quickly change them. Okay, so the second tower has the highest tube at 88. And then we want to put that core height at the middle of the list. The first 4 values coming in here and the second 4 values coming in here. But since we are flattening the inputs here, we actually end up with one list of 18 values. We need 2 lists of 9 values. So we need to change what happens here. Here we have already 4. So I'm going to stop this flatten. I'm going to stop this one as well. And let's try stopping that one. What do we have? Yeah, it's still not the right thing. Basically here we have a tree of 2 lists with 4 values each. Then we want to add this tree of 2 lists with 1 value each. And then this one. But if we pay close attention, the paths on these lists. A path is the address of the branch in a tree. So here we have 0, 0, 0 for the first branch and 0, 1, 0 for the second branch. Each of them has 4 items. And here we have 0, 0. 1, 0 is missing. And the second one is 0, 1. The third input is the same as the first one, 0, 0, 0 and 0, 1, 0. A way to solve this is by simplifying the 3. Simplifying will remove all the unnecessary zeros, so it will end up with 0 and 1 in this, 0 and 1 in this one, and 0 and 1 in this one. At the end we have one tree with two branches. The address of the branches are 0 and 1 and 9 values for the heights of the tubes in each of them. So we fix that, and then this goes in then to the calculation of the actual heights, where we multiply it by the floor height, and it goes into extruding the tubes. Is that correct? Let's see. We have 9 curves, two lists of 9 values each, and at the end we have still split into branches the two towers, let's say. So far so good. We basically don't need this slow area calculation, since we're calculating the area with the formula. Let's see if that is still working. Going down to the floor area, yeah, we have two values for the area, one for the first tower and one for the second tower. So that's fine. They are in their own tree branch here. Then we need to check if the shadow is working. So here we have the shadow calculation. Basically this here will fail. Well, it would not deliver the results we want, since the mesh casts the shadow. But when we union all the shadows, let me preview that. So for each tube we get its own shadow, and then we want to union only the corresponding shadows for each of the two towers. Instead of flattening here, what we basically need to do is, simplifying will also not work, we need to remove one branch from that tree. Let's look at what we have. Basically we have each of the shadow in its own list, in its own branch, and the address is 000, which would be the building address, so to say, and then we have 0 or 1 or 2 or 4 for the shadow address. And we can use here the path mapper. The path mapper allows us to restructure trees, just changing the data structure, not the data itself. We can create a null mapping, and this will correspond to 0, 0, 0, 0 for the structure of our map. And in the result, we actually want to remove one of these branches. So we kind of partially flatten that tree, not completely into one list, but into two lists. Let's see what we have at the end. We can show a panel, use a panel. And it seems like exactly what we want. One list of 9 polylines, the shadow outlines from the tubes of the first tower, and one list and a second list with 9 polylines, which are the shadow outlines of the second tower. So we can connect that here and remove the flatten. And now here we should have two curves, basically. So let's stop that. We have two curves. One is for tower 1 and the second for tower 2. And as well, we also have two areas which are calculated for each of the curves. We have two region intersections for the shadow of the park and two region intersections for the shadow of the neighbor. So from now on, our definition seems to be working with these slight modifications. Let's check here. Yeah, we have 2 times the floor area, 2 times the shadow area, 2 times the park overshadowing, and 2 times the neighbor overshadowing. So now we have 2 towers. Once we modify the definition like that, it shouldn't matter if we have 2 or 200. So I'm going to shift connect one more set of sliders and quickly set it to alternative values. And now we have 3 values for each of the criteria we evaluate on. Okay, so now we have kind of a model that works with multiple designs. but it's pretty difficult to see what the designs are, how they look, and also pretty difficult to see which of these values belongs to which design. So next we are going to build a grid system to display all these options next to each other and also have the corresponding values written next to them. That will help us then later on browse and sort and select the design solutions that are actually good according to our criteria. So we're going to start by building a square grid to display these options. Let's place this here at the end of our definition. So I'm going to double click square grid, and for the size of the grid, let's take a big number, something like 300. So that would be the distance between each design options as we display them next to each other. And we need two sliders for, let's start with 4 and 4 for the size of this display matrix. Okay, so if we now zoom out a little bit in Rhino, we would expect to see a tower in each of these grid points. All the towers are generated at the 0, 0. So basically we can take them and move them to the corresponding location. Here we have the points to where we want to move. I will put them in their own component and flatten this. And where are the towers? They are all the way here in this geometry component. But since each tower consists of 9 tubes, it will be easier for us to move them together if we group these objects. So what we have now is a tree with 3 branches, and each branch contains one group with the 9 tubes. So let's take this and put it closer to our grid system. So we'll be moving these objects. Let's take and move. And we'll be moving them with the vector that's actually made by the point. And here we go. Okay, something's wrong here though. The first thing we need to do is to flatten the list of the towers. So let's take in, so that's our geometry. And we need to flatten it so that in the move component lists are coming in and in both the geometry and the vectors. But then the other thing we need to do is that to match the number of grid positions to the number of towers. At the moment we have only 3 towers and 25 grid slots. Later on we'll have thousands of towers and 25 grid slots. So we need to deal with a situation where either the grid slots are more or the towers are more. We could do that by finding the maximum or the minimum of these lists. So let's find the length of the list from the grid positions and also the length of the list of the design options and find the minimum of these two. This will be the minimum number. It should be 3 in our case. Yeah, it's 3. And then let's split both lists. Split both lists with this number. So in A, we will have the right amount of slots for the right amount of towers. We also need to do the same split the towers with this number, and it should give us 3 because there are only 3. Oh, wrong. I connect them in the wrong location. Here we go. Okay, so see what happens now. If I change the grid size, okay, 1. If I reduce also this one, then the tower will disappear, and at one point we have nothing. So if we stop the original, if we stop the preview of the original models here, the unmoved ones, then, and I think also somewhere else, we have that over here. Preview off, and here we have the 3 design options that we currently have defined with the 3 sets of sliders. Let's also display the shadow that each tower throws next to its shape. The shadows are here. We can simply copy that and connect it. Then we can also flatten it and split the list in the same way, the list of shadows, to the maximum number of slots available. And we also need to move the shadows from their original locations to the location where we want to preview them. So now if I hide the preview of the shadow here and here, we'll only see one shadow per design option. Okay, we can group that as our matrix of tower options, matrix of options logic. And let's see how we can display then all the values we've calculated for each of the design. To do that, we're going to use the text tag component, text 3D. Yeah, this one, text tag 3D. It takes the location of each tag, then it takes the text to display and the size of that text. So the location of each tag is our filtered points. And then let's start with the dummy text here, test, just to see if things are displaying correctly. And let's make a size of 10. Here we have it. The text is displayed under the tower. Let's move that using the justification option. We want to go top left. Yeah, so it's out of the underneath the tower. So test, test, test. Now let's feed it with the right numbers and text we want. First we want to display the area, then the park shadow, and then the neighboring shadow. Let's merge all of them into one component. So that would be the park shadow and the neighboring shadow. Here is the total area of the shadow, and we need one more up for the area of the building, which would be here. Here we are, area of the building. And now we have again the need to simplify these trees so that they're properly matched. So let's simplify the inputs. And we have a tree of 3 branches and 4 values per branch. The total area, the shadow area, park shadow, neighbor shadow. If we try to pass that over here, they will get displayed on top of each other. So basically we need to turn it into one text object. And we can do that by joining, text join, all these values into one text item. And we want to have them on separate rows. So I'm going to bring in a panel, and the panel will contain just a new line character. So I basically pressed enter once in that box. Let's preview what we have. Let's get in another panel. It is what we want. We have one item with an index of 0, but the text is in 4 rows. And let's connect that to our text component. There is some kind of a problem. We forgot to flatten that input. So let's use a generic data component to flatten it. And the other thing we need to do is also to filter it to the maximum number of towers or maximum number of slots. whatever is the case. So here we have it. We have 3 towers, pretty cryptic set of numbers. So let's see if that could be improved, but they are the corresponding numbers. And what we would like to do is to put in front of each number what it is. So I'm gonna bring in a panel and type that, total floor area, then shadow area, then park shadow and neighbor shadow. Very important in order to be able to use that. Right click and set the data multi-line to off, so that Grasshopper treats each of these rows as a separate data. And then we want to concatenate, is the operation for adding texts together. It's like the plus sign for texts. Concatenate this with that. And let's see what we have, and then pass that over. Maybe having an interval here will help. So I'm gonna zoom in, type in interval behind each of these. Yeah, so we have a bit of space there, but basically that already gives us an overview of what each of the numbers is. Okay, so let's group that into, we don't need this. This is something we need. This is the enter sign. This is also something we need. These are the labels. Let's group that into one group for our texts. This is the data. Text labels. Now that we've built the system to preview multiple options, let's see how we can actually more systematically generate these options. For now, we just have the 3 arbitrary sets of sliders. And we can substitute them with something that's a bit more exhaustive. We can think of it like this. Tube 1 could have multiple states. Tube 2 can also have multiple states, multiple heights. For each of the states of tube 1, we want to build an option of the tower matching all the states of tube 2. The same for tube 3, tube 4, tube 5, and so on. The number of combinations can quickly skyrocket, so let's start only with 2 or 3 states per tube. The lowest one somewhere towards the middle and the highest one. We can build that by using the series component. So let's quickly copy that model down and disable it. Then we can come here and delete all the sliders. For now, we won't need them. No towers. And let's start building that combinatorial parametric setting. So we can use the series component, and we said we want 3 states. So let's say we'll start at the 30th floor. That will be the lowest. So this is our starting point. We are going to have a step size of 30 as well. So the next option will be at 60 and the next option at 90. And we'll stop there. So basically we want a count of 3. That will be 30, 60, 90 for now. So this will be all the states we want for each of the tubes. And now we need to create all possible combinations of all possible tube states for tube 1, 2, 3 and all the way to 9. That would be created for us by the cross-reference component. So I'm going to create 8 states like that. So cross-reference will give us all the combinations for 8 items, each having 3 states. And these are 6,561, already quite a high number. Let's see how we can use that in our model. Since the combinations are quite a lot, 6,500, let's first disable something here. Let's disable this vector so that the building of the 3D model of the towers doesn't run at the start when we start connecting them, because things will get quite slow with this number, with this high number of designs. So let's connect all of the outputs to the list, to the merge component. You already see that that's quite laggy. and our profiler tooltip here tells us that that's taking 1/10 of a second to calculate, and the sorting is also taking a lot of time, and so on. But we generally have now, at least numerically, described all these 6,500 states. And even we have all their floor areas calculated because the area is running. To reduce the number of designs, let's filter them on area. Let's create a quick filtering logic here. So if the area is larger than, let's say, 320,000 square meters, then we want to keep that. So this would be our area here. That would give us the filtering mask, and we can call with that mask. So if it's larger or equal, we want to keep the option. Now all the options are here, but they are described with 9 numbers. We need to find a way to put the 9 numbers somehow in one object, and we can, to do that, we can, let's delete this panel. To do that, we can use the text. So I'm going to join them as if they were texts. I'm going to join each of these 9 states, and I'm going to join them with a dash in between. So here we are. How does that look? Let's see if we can display it. So for each tower we have, okay, the first combination is 30, 30, 30, 30. Each tube is with the 30 high. Then we have 60, 30, 30, 30, 60, 30, and so on. All possible states combined into one string. We can call that even the DNA of our buildings, the genome of our buildings. So this is what we are filtering. And once we filter them, we are down to 1,700. Then we can do the reverse. We can convert this text back into numbers, text split, and this would be the text to split, and we're splitting it with the same character with which we combined it. And that's something that we can use as our new heights. Let's take in a number, integer number, and call it heights. We can connect that back over here, where just before the extruding command. Let's also disable now the geometry and enable the extruding command, save our work, enable the extruding command by enabling the vector for extrusion, and see if that would work and how long it will take. Okay, that took some time to calculate, and we can see also the time here, that close to 50 seconds for the extruding and close to 50 seconds for the capping. One way to speed this up is to remove all the empty branches from the tree of the heights. So we will do that first. And the second way to speed this up will be to start using meshes for the 3D model of the towers instead of the extrusion and capping, which is NURBS modeling, a bit slower. Meshes actually make sense because it will also avoid the converting to meshes we have to do when we're calculating the shadow, so it will speed up the model altogether. So let's first remove the empty branches. I'm going to come here just before the heights and getting the component clean tree, and the last parameter here is the tree which we want to clean. It removes the null branches or the null items, it removes the invalid items, and what we also want to enable is to remove the empty branches. So I'll right click, set the boolean to true, and that would give us a smaller structure. If we observe here, we have still 405 values, which come from the way we filter based on area. Currently close to 400 square meters is our filter threshold, and 405 values, but a lot of branches. Here we have way less. And connect that here. and as you see, that already calculated. We didn't have to wait. So Grasshopper treats the empty branches somehow not very effectively, but still I think we can lower these numbers even further by using a mesh model. If I enable the geometry component here now, we will also be able to take a look what happens later on when we come to the shadow. Here we have another half a second, here we have another half a second, and so on. So everything that we can reduce will speed our model later on. Let's call that 3D Tower NURBS. Okay, so let's build the tower as a mesh. We're going to use the box mesh component for that, mesh box, which needs a box and then the number of faces along the X, Y, and Z. The number of faces will be 1, so our mesh is really with minimal geometry. And then the box we will get with the box domain box. The domain box requires a plane, and then the domain along X, Y, and Z, how big that box is. Domain means a range of numbers from 2. Our base plane is actually the middle of each of these squares. So let's take the squares which are here. If you're not sure what is where, you can enable the preview only selected items, and then when you have them selected, you will see only what's selected. Here is the towers, here's the curves. So this is what we need, and let's use the area component, which gives us not only the area but also the centroid. There they are, and use the centroid for the base. So we have the bases. Now along X and Y, the domain will be starting from minus the half of 23, minus 11.5, and going to 11.5. So let's do that. Here we are just going to bring is we're going to bring the 23 first here in the area where we are working, and then we're going to divide it by 2. So we get the 11.1, and then we are constructing a domain. I'm going to connect 11.5 here and right click on A, set an expression minus X, minus whatever number is coming in. So that would make minus 11.5 to 11.5. This will be X and Y domain, and our Z domain will actually be the height of each tube, which comes in from the number of floors the tube has multiplied by the floor height, so this number here. Okay, we have the boxes, and now we can connect that here. As you see already, the generating of this took only 13 milliseconds compared to 2 times 400 milliseconds, so way faster, and we can use that here. That would also save us time in the converting in the shadow component, so 100 milliseconds saved there as well. And we can disable this NURBS 3D model. Actually we need the curves, so let's exclude them from the group and disable the rest. And this would be our fast mesh based generating mesh 3D model. Okay, so now we've sped up our 3D model creation. Let's hide everything here, preview off, and increase the number of slots we have in our grid of options. So let's go to 4 by 4 or 5. Here we are, a lot of options. Each option is displayed with its shadow. They are all different, and next to each option we have also the parameters that we evaluated for the option, which are the area, the shadow area, and the overshadowing of park and neighbor. However, you can see that it's very difficult to find what you're looking for. We need some way to sort, we need some way to browse through all these options based on different criteria. And that's what we are going to do in the next episode. See you there.